A single crystal, grown in China, wider than any silicon carbide boule currently sold commercially anywhere in the world. The company is Tiancheng. The diameter they report is 14 inches, wide enough to fill a dinner plate. And the established cadence of the entire silicon carbide industry said that number was not supposed to exist yet. The industry has moved methodically, 4-inch to 6-inch to 8-inch, with 8-inch only now entering volume production, and 12-inch still in development at the incumbents. 14 inches is beyond the current commercial frontier. Before you assume this is a render on a slide deck, it almost certainly is a real crystal. Growing silicon carbide to that diameter is a genuine materials achievement. The question is what a real crystal of that size actually proves, and what it does not. Because there is a word sitting in every headline about this result, and that word is reported. What independent verification actually exists, and why that gap matters, we will get to. And there is something else. Growing a crystal 14 inches wide requires a seed crystal nearly that wide to begin with. Where that seed comes from, and who controls that upstream node, is a thread worth pulling. There is also the furnace itself, the thermal control problem that gets harder, not easier, as the boule gets wider. That detail will make more sense once you understand what yield actually means at this diameter. This is not really a story about one crystal. It is about whether raising the diameter floor is enough, or whether the ceiling, defect-free yield across the full width, is what actually governs the game. Those are two different problems, and right now, only one of them has been demonstrated. To understand why 14 inches matters at all, you need to understand the economics that make diameter the central lever in this industry. Silicon carbide is not silicon. Growing a silicon ingot by the Czochralski method, the standard process for computer chips, happens at rates measured in millimeters per minute. Silicon carbide, grown by physical vapor transport, grows at rates measured in tenths of a millimeter per hour. That is not a rounding error. That is a fundamentally different relationship between time, capital, and output. A single boule takes days to grow. The furnace runs continuously. The energy cost is high. So every wafer you slice from that boule carries a meaningful share of a very slow, very expensive process. Now think about what diameter does to that equation. Moving from a 6-inch wafer to an 8-inch wafer increases the usable area of that disk by roughly 78%. You're not running the furnace any longer. You're not adding more powder or more seed. You're simply harvesting more surface from the same growth run. Think of it like a printing press that takes 3 days to reset between runs. If you can print on a wider sheet without slowing the press, every extra inch pays for itself on every single run. That is what diameter does to silicon carbide economics. And because each electric vehicle traction inverter uses multiple silicon carbide dies, and those dies come from wafers, which come from boules, the substrate cost is a direct input to inverter cost, which is a direct input to vehicle margin. The connection runs all the way from the furnace to the sticker price on the car. So the objection is obvious. Why not just run more furnaces instead of chasing bigger wafers? You can. But furnace count scales linearly with cost. Diameter scales the output of every furnace you already have. At constant yield, larger diameter wins the per die cost calculation every time. The critical phrase there is at constant yield. That condition is where the whole story lives. What does it actually take to grow a crystal 14 inches wide? Not just wider than 6-inch, wider than anything currently in commercial production, anywhere. 3 nodes compound on each other, and none of them is trivial. The first is the seed crystal. Physical vapor transport is not a process you can start from nothing. The seed crystal, The small piece of silicon carbide you place at the top of the furnace to initiate growth must be close to the diameter you intend to grow. That is a physical constraint of the process, not a design choice. To grow a 14-inch boule, you need a seed that approaches 14 inches. That seed is itself a product of prior growth. It has to come from somewhere. Whether Tiancheng's seed for this result was grown domestically or sourced from elsewhere is not publicly confirmed. That upstream node, who controls the seed supply at this diameter, is genuinely open. The second node is the furnace. Growing a wider boule does not simply mean building a bigger chamber. It means maintaining temperature uniformity across a wider cross-section at the extreme temperatures silicon carbide growth demands. Imagine baking a soufflé in a pan 3 times the diameter. The oven that worked perfectly for the small pan may have a hot center and cold edges on the larger one. A soufflé that rises in the center and collapses at the rim is not a successful soufflé. At 14 inches, the radial thermal gradient problem is steeper than at 8 inches. The center and the edge of the growing crystal see different thermal environments unless the furnace geometry is specifically adapted to compensate. That is where defects nucleate. Tiancheng's specific furnace design at this diameter is not publicly detailed. The third node is the powder. Silicon carbide growth starts with silicon carbide powder, the feedstock that sublimates and deposits onto the seed. The purity of that powder directly affects the defect density of the crystal it produces. China has developed domestic silicon carbide powder suppliers, and that supply chain has scaled meaningfully over the past several years. But full self-sufficiency at the purity grade, a leading diameter crystal demands, the grade that keeps defect counts low enough across a 14-inch width, is not confirmed. The domestic capability is real and growing. It is not yet complete. So what does Tiancheng's result actually demonstrate against that backdrop? Growing a 14-inch silicon carbide boule, even once, even at unverified yield, is a real step at the growth node. The capability to initiate and sustain a crystal at that diameter exists. That is not nothing. Every commercially dominant silicon carbide substrate that Wolfspeed or Coherent has ever shipped also began as one grown crystal in one furnace with no yield data attached to it. The first result is a prerequisite for the second. But there is a distinction the result does not erase, and it matters. Growing a single boule, running a repeatable production process, and producing commercial-grade wafers across the full diameter at consistent yield, those are 3 different milestones. The first appears to have been achieved. The second and third are unconfirmed. When the input here assesses the crystal growth node as bypassed, that means the growth capability is demonstrated. It does not mean device-grade wafers are shipping. The furnace thermal control node and the powder feedstock node are assessed as partial. Progress is real, completion is not. That is the honest ledger, which brings you to the thing that actually decides who wins at this diameter. And it is not the number on the boule. It is what you can reliably cut from it. In silicon carbide, the critical defects have names: micropipes, basal plane dislocations, stacking faults. They are not distributed evenly across a boule. They cluster, and under radial thermal gradient stress, the stress that increases as you push diameter wider, they cluster toward the edges. The outer ring of a wide diameter boule grown without precise thermal control is where device-grade yield degrades first. A die cut from the edge of a poorly controlled 14-inch wafer may fall outside the defect threshold that a power device can tolerate. It skips, to extend the analogy, like a vinyl record pressed on a larger platter where the pressing machine loses consistency at the outer tracks. Every silicon carbide die cut from an edge zone with excessive defect density is a skipping track. It is substrate area that grew but did not yield. Wolfspeed has spent roughly 2 decades optimizing exactly this number, the share of wafer area that falls below the defect threshold at commercial scale. Their process knowledge is not expressed in diameter headline records. It is expressed in yield maps, in furnace recipes, in the incremental process changes that moved their defect density downward across 4-inch, then 6-inch, and now 8-inch wafers. Coherent has done the same. The current confirmed commercial leading edge is 8-inch, with Wolfspeed ramping volume there. 12-inch is in development. The process knowledge that underlies those ramps is deep and specific, and slow to transfer. Tiancheng's yield at 14 inches is not publicly confirmed. The ceiling is still well above the floor. The objection surfaces here. If 14 inches is this hard to yield, why not perfect 8-inch first? The answer is partly strategic and partly practical. Demonstrating diameter leadership signals capability trajectory to customers, investors, and domestic policy. It changes how negotiations with foreign substrate suppliers are conducted, even before domestic yield is optimized, and the learning curve on a wider boule, even at low early yield, feeds back into the process optimization that will eventually raise that yield. You do not arrive at high yield at 14 inches without first growing at 14 inches badly. Now, what does the evidence actually show? And what does it not? Tiancheng's 14-inch crystal is reported in trade press and appears to be a real crystal growth achievement. That is the credible part. What is not confirmed? Independent defect mapping of the result, device-grade yield across the full diameter, production volume, run count, and whether the seed crystal was domestically sourced. The word "reported" in the opening was deliberate. It carries weight. A real crystal grown once and a commercially yielded product at consistent scale are 2 different claims. That is not contradiction. That is precision. The honest position is that the first is credible and the second is unverified, and treating either as the other distorts what the result actually means. Step back further and the context shifts. China is the world's largest electric vehicle market by volume. The silicon carbide substrates that feed its domestic power device manufacturers flow heavily from imports, from Wolfspeed, from Coherent, from Japanese suppliers. The cost of those substrates is a real input to inverter cost, which is a real input to vehicle economics for manufacturers operating on thin margins at high volume. A domestic silicon carbide supply chain that can grow wider crystals, even at imperfect yield, changes the cost negotiation with foreign suppliers. It does not eliminate the import dependence immediately, but it shifts the leverage. When domestic suppliers can credibly demonstrate a diameter beyond what foreign suppliers currently sell commercially, the conversation about pricing and supply security changes. And as yield at that diameter improves, the economic floor of the entire domestic supply chain rises with it. Raising the floor does not require reaching the ceiling first. It just requires that the floor be real, repeatable, and improving. Multiple domestic Chinese silicon carbide companies, Tiancheng, SICC, TanKeBlue, and others, have been scaling in parallel. The precise domestic market share versus imports at current commercial diameters is not confirmed publicly. But the direction is clear. A supply chain that began largely dependent on foreign substrates is building toward a broader domestic capability, with Tiancheng's 14-inch result representing the leading edge of that diameter push. Here is my honest read. The triumphalist version of this story says China has leapfrogged Wolfspeed in silicon carbide, and that is not what the evidence shows. The yield ceiling is real, Wolfspeed's process lead is real, and a diameter record without yield verification does not transfer directly into commercial advantage. But the dismissive version, that this is a lab stunt with no commercial meaning is also wrong, and wrong in a way that materials history does not support. Every commercially dominant silicon carbide substrate ever sold began as exactly one grown crystal in one furnace with no attached yield data. The first result is not the product, it is the prerequisite. What the evidence actually shows is a company that has demonstrated a real growth capability at an unprecedented diameter inside a domestic supply chain that has strong structural incentive, the world's largest electric vehicle demand base, to close the yield gap against incumbents whose lead is genuine and expressed in process knowledge that degrades slowly, not in a wall that holds forever. The floor is rising. The ceiling is still well above it. The distance between them is the only honest measurement worth making right now. Wolfspeed's advantage lives in 2 decades of yield optimization, process knowledge that is hard to transfer and slow to replicate. But China's silicon carbide supply chain has captive domestic demand from the world's largest electric vehicle market, pulling it forward at a scale that creates relentless commercial pressure to close that distance. Which matters more at this stage, the depth of the process knowledge gap, or the scale of the demand signal working to close it? Drop your honest answer in the comments. I read them. If you want to follow exactly how the yield data at 14 inches starts to emerge, and what it will mean for the domestic cost floor when it does, subscribe, because that is the next chapter of this specific story. One crystal, grown wider than anything in commercial supply. The floor is up. The ceiling is the story.